Algebra 2, solve linear systems by graphing and solve algebraically. A system of two linear equations in two variables x and y is called a linear system, and it consists of two equations that are usually written in standard form, ax plus by equals c and dx plus ey equals f. That isn't always the case, but it is often. A solution of a system of linear equations in two variables is an ordered pair x and y that satisfies each equation, which means if you plug in those numbers x and y into both equations, you'll get true statements. If you were to graph them, solutions correspond to a point where the graphs of the equations in a system intersect. So let's start with a system with one solution. We're going to solve this by graphing. So you might have done this in Algebra 1 and graphed by hand. We're going to graph using technology. So we're going to use the TI-83 or 84 graphing calculators. I'm also going to show you in these notes how to use Desmos.com, which is a great tool. So let's start with the graphing calculator. We've got the system 4x plus y equals 8 and 2x minus 3y equals 18. So start by solving for y with each of those equations. So you get y equals negative 4x plus 8 and y equals 2/3 x minus 6. So now let's put these on the graphing calculator and see if they intersect. So on your graphing calculator, go to your y equals menu. And this is where you can enter equations to graph. So we'll type in negative, so use your negative sign. For a variable, you use this key, pressing it once, you'll get an x plus 8, and then arrow down to your second equation line. We'll just say 2 divided by 3, x, and then minus 6. Now, up here in the right, press graph. If you don't see a nice graph like on my screen, press zoom and then 6. And that should reset your graph space. Notice that we have a point that's crossing at 3, negative 4, or we have a point of intersection. You can use this trace feature and you can arrow down and see if you can get it to land on 3 and see if we have the point 3, negative 4. If it won't quite settle on 3, you can actually just hand enter 3 and press enter, and then you'll see the y value that matches with it, and it is the point 3, negative 4, and we do see that that is a point of intersection. So that means that this system does have a solution. It is the point 3, negative 4. We're going to talk about how to classify systems. So a system that has at least one solution, like the one we just looked at, is called consistent. If it has no solution, we call the system inconsistent. Now, if it has a solution, so it's consistent, then if it has one solution, we call it independent, and infinitely many solutions, we call it dependent. So the system we just graphed intersected at 1.3, negative 4. So that means it is a consistent system because it has at least one solution. And because it has one solution and the lines are distinct, we call it an independent system. So consistent and independent. So look at the graphic. These shows our three different situations for solving a linear system. We can have exactly one solution, like we just did, where lines intersect at one point. We call this system consistent and independent. We can have a system where the lines intersect in many places. They graph right on top of each other. The lines coincide. This is consistent, but a dependent system. And then we can have lines that are parallel, that don't intersect. That means they have no solution, and we call those inconsistent. So these are just some vocabulary, some classification that you'll need to memorize. Now let's solve a system by graphing, and we're going to use Desmos. The nice thing about Desmos is that you can enter it in standard form. You don't have to have your equations in y equals form. So you're going to go to Desmos.com. And then you can just start graphing. So we'll type in these two equations. So we have 4x minus 3y equals 8, and 8x minus 6y equals 16. Notice that we only see one line, and I'm going to take away the second line, and I can see the first line is just below it. So these are virtually the same line when graphed. So now we have a system that has many solutions. We say infinitely many solutions. Since it does have at least one solution, we say it's consistent, but since the lines are not distinct, then we say it is a dependent system. Let's use Desmos again, and let's graph these, and you'll see what it looks like when you have a system with no solution. When you're looking at those equations, you might notice that something kind of looks strange anyway, because they're virtually the same except for the constant. Because we have 2x plus y equals 4, and then 2x plus y equals 1. So what happens is we have two lines with the same slope, but two different y-intercepts. They will never cross, so they have no solution. They are parallel lines. So this system is inconsistent, and that's all. We don't go on to the second part because we don't have any solutions to talk about to see if those lines are dependent or inconsistent. Sorry, independent or dependent. Now let's talk about solving systems not by graphing, but by using algebra. So you most likely have learned these before. There's the substitution method. So you're going to solve one equation for one of its variables, substitute that expression into this other equation, solve for the single variable, substitute again, and find your point of intersection, the solution. For elimination, you're going to multiply one or both equations by a constant so that when you add or subtract the equations, one of the variables will eliminate. Then you can solve for the other variable, substitute into one of the original equations, and find your point of intersection, if there is one. So let's solve this one using substitution. I'm going to pick the second equation and solve for x. Then I'm going to take that expression, what x equals, and substitute it into my first equation. I'm going to do the math to solve for y. So y equals -1. I'm going to plug that into either of my original equations, and I like to plug it into the one where I have rewritten, in this case, what x equals. So I get 2 plus 4, or 6. So these two lines will intersect at 1 point, 6, -1. I can check that by plugging that into both of my original equations and seeing that I get true statements. So this system is consistent because it has at least one solution, and independent because it's intersecting in 1 point, so that means it's two distinct lines. For this system, I'm going to choose my first equation and solve for y. I like to pick the variable that just has a coefficient of 1. So I'm going to take that expression for y and plug it into my second equation, solve. Now I notice something is strange, but I just solve all the way and I get a true statement because 0 does equal 0. So that is an algebraic clue that these lines are virtually the same. They will graph right on top of each other, so I have infinitely many solutions. Since I do have at least one solution, this system is consistent, but it's dependent because there are not two distinct lines. Now let's talk about elimination. So I examined my two equations and notice if I multiplied my second one by -2, then I would get a -10x, which is opposite from my 10x in my top equation. And then I can add those two equations. I have to add each part, so I get -8y equals 40, and then y equals -5. I'm going to substitute my -5 into either one of my original equations. I just pick the top one and solve for x. It's all right if you get a fraction. And so we have a point of intersection at 3/5 -5. Since there is at least one solution, this system is consistent and independent, because if it's intersecting at just 1 point, I know those are two distinct lines. And now finally, let's solve this one using elimination. So I'm going to multiply the top equation by +2. And then I get 6x and 6x, so I'm going to subtract. I have to subtract every part of these equations, all three parts. So I subtract the x's, the y's, and I get 0 equals 18. That is not a true statement. So this is an algebraic clue that this system has no solution. These lines would be parallel. So it is inconsistent. All right, this concludes the notes for solving linear equations. Sorry, linear systems.